First perfect frame that we saw is data frame. The second one, this actually it is a special frame, is a remote frame. After that, we have a third type of frame, that is error frame. The error frames, we have two division again, active error frame and passive error frame. Actually, error frame, it used to have an active error flag and passive error flag. The active error flag is 6 dominant bit. Passive error flag used to have 6 consecutive recessive bit. The error frame used to have 6 dominant or recessive bit plus 8 recessive delimiter. 8 recessive delimiter. Otherwise, we used to call as a terminator for that error frame. The terminator of the error frame, otherwise the boundary of error frame, is 8 recessive bits. To identify, to denote what type of error it is, we have 6 consecutive dominant in case of active error and 6 consecutive recessive bits in case of passive error. We have like that. Clear? The error frame will be transmitted when there is a bus error. When there is a error, like we told, right, some 12 rules. If any one of those rules fails, there will be the node which detects it that will publish in the bus for other nodes that I have detected an error. To denote that, it used to transmit. Updating internal error count is the internal process. And then transmitting the error frame is communicating to the world. For example, when we have a function in our home, wedding or something like that, we used to internally, we will communicate to our family members. Again, when we want to publish it to the entire, the people of city or town or country, we will put that in the newspaper. Similar to that, when there is an error condition, each node will update its internal error counter. At the same time, they will make the other to understand that there is an error by means of transmitting error frame. As I told you before, the error frame has two types, active error frame and passive error frame. When it will become active error frame? When the internal counter error count of ECU is less than, either it is maybe transmitter error count or receiver error count. If any one of them is less than 128, that will be considered as an active error frame. In that time, the node used to transmit active error frame. When error count crosses 128 and less than 255, they will send the passive error frame. When the error count exceeds 255, the bus off will occur. So bus off is a state in which the node will terminate all its message transmission, and then it will go to a state called a bus off. In that state, it used to be there for around 120 minutes, I believe. Till that time, it will be in that time. It won't take part in network. After 120 minutes, it will wake up and then will try to retransmit. This is how the bus off used to work. Then another special frame. The first frame is data frame. The second frame is an remote frame. Third is an error frame. Fourth is overload frame. Overload frame and your active error frame, both are same. It used to be, when you look into that, the structure wise, overload flag also used to have 6 dominant bit and then 8 recessive bit delimiter. Again, your active error also will have the same. But only thing is, the overload frame will be transmitted by the receiver only. But error frames are not like that. Error frame will be transmitted by every node. But when a node is overloaded, it used to communicate the transmitter like I am overloaded. So you can transmit the message after some time, something like that. For that, this overload frame will be transmitted. So only who is transmitting it, that matters. Based on that, the overload frame used to have 6 dominant bits and then 8 recessive bit as a delimiter. It is also a fixed structure frame. So you won't have any dynamic data in the overload frame as well as error frame. They used to have a fixed structure. That is about overload frame. Then interframe spaces. We have arbitration process to avoid the collision. But at the end, every packet which is going out from a transmitter, they used to go serially only. Bit by bit only, they are shifted. The data are shifted as a voltage pulses. Every CAN packet in the CAN bus is like a compartment in your train. In a lengthy train, in between every compartment, you used to have some small space. Why don't they make a complete compartment as a straight line? Why they are making them as? Why don't we have a single compartment for a complete train? The reason is when it comes to bend or something like that in the pathway, having like this will help them. That's why they have those sort of structure. That is what my understanding. But anyhow, every compartment used to have a space. In a train, in between compartment, we used to find a space. Similar way, the CAN packets are also like a compartment. Each compartment used to have some 64 bits of data, right? No, they are going like a train, one after another. So in between every CAN frame, there will be, though they are going with whatever the speed might be, whether you may send it to 500 kbps or 250 kbps, whatever it is, but there will be a small period of time, there won't be any bit transmission. That is called as interframe space or intermission. It is 3-bit timing. That means if you transmit a 3 bits in a serial bus, how much time it will take, that much of time will be used as an interframe space. The every packet, CAN packet has a space in between that. Because of that, there is no possibility of collision. If we don't have that gap, the receiver can misunderstand, it can sample it in a wrong way. There is a possibility of misinterpretation of CAN bits. To avoid that, every CAN frame in the CAN bus used to have a space with a forward packet. So there will be a space in between them. That is called as interframe space. The size of interframe space is 3 recessive bits. So when you transmit a 3 recessive bits, how much time you used to take? That much of time. They will keep the bus to idle for that time. That means there won't be any transmission in that time. The bus will come to recessive state, 2.5 volt state for a short period of time. Like that, they separate, they protect the CAN packets from the collision. Is that clear? Why we need interframe space? What is interframe space? Why we need that?
To avoid the collision between the frames and
To avoid the collision, we have arbitration. To avoid a collision only, we brought an arbitration process so that only one will go. This collision means what?
to overlap.
Overlapping one message with another message packets. Because, let me draw a diagram so that you will get some idea. Okay, function escape. I pressed escape, but it is not doing. Okay. See, when you take a complete packet, it used to have a startup frame, which is an active low, and then a series of bits. So I am drawing only can I, right? You assume in a complement of this is in the other side. So this is my voltage pulse. But immediately, this is one frame. From here to here is one frame. If I start in another frame, immediately in this place, with a startup frame and other stuff, what will happen means, assume there is a fluctuation. Because of that, the receiver is reading it from this place. So there is a possibility of misinterpretation. It will sample in a wrong way. That's why what they do after completing an end of frame, they maintain a fixed gap. In that time, no node is allowed to transmit. That is what beauty here. When you have an interframe space, no node is allowed to transmit in that period. Everybody should keep quiet. It transmit one packet, they are waiting for a second, wait for 3 recessive bits, and then they will do the next packet. This happens every packet which goes out from the transmitter side. The receiver also will take a packet and wait for a 3 recessive bit timing, and then it will accept the second packet. It's just like train compartment. They will accept one compartment, and then they will wait, then they will accept next compartment. Like that it works. So it's not a continuous serial train which is going from transmitter to receiver. That you have to understand. For that only, the interframe space come into the picture.